3. Muy buenas tardes a todas y todos en esta nueva y última sesión de Mix para el mundo. Vamos a seguir o vamos a continuar. Eligen. Vamos a seguir con el trabajo que se está realizando con el fin de terminar con la adaptación de impedancia, ¿cierto? De nuestro LNA. Y arreglar cosas como las que está mostrando ahí Miguel, que por ejemplo el rendimiento en la banda de utilización tiene ese pic de ganancia que es un poco no deseado, digamos. Entonces, ahora Mikko nos va a iluminar con todas las técnicas para... You will brighten the path, the enlightenment, the path towards enlightenment. Yes, we are. If you guys, and the mic works well,
but then you will lose it. So everyone can meet Mikko Varonen.
Hello.
Good turn.
Okay. So last session we made the noise matching of the LNA, of the two-stage LNA, and now we are having a mysterious plot here, but in a red color we can see the noise temperature of the LNA. So we were simulating that we should achieve somewhere around 10 kelvins or below at 40 gigahertz based on the TCAS min and the NF min simulations. And it seems to be that we did a correct job, so we are having that noise at 40 gigahertz, so a bit below 10 Kelvin I see. And okay,
You let me only one.
Yeah, please.
One quick thing is that you can find at the web page the new transistor model with a solved problem with the temperature and the last transistor design at the third section. So in this one, we will do the fourth session and we will upload it also. So you can also play with this one at your own computers. And I suggest you to do it now. So also Mikko can help you in doing the design. So here you have the current one we are going to work with now. And so please continue.
Okay, can you put back on the result? And Miguel has also plotted the minimum noise temperature possible to achieve, and that also suggests that we are matching to the correct impedance, since we at the 40 gigahertz amplifier noise temperature and this NF min are on top of each other or close each other. Then the expected gain was around something around 7 dB for the when we match it for single transistor, if we match it to optimum noise. So for two-stage amplifier, it should be somewhere 14 dB or less, and that is also there. But the ugly thing is that peak at 20, somewhere 26 or 25 gigahertz. And also in the stability factor simulation, we can see that it is unstable. Do you have that one? So around 20 gigahertz, we have a problem in the stability. So most probably if we would do it this way, we would have an oscillation at 20 gigahertz in measurements.
Only to let the people see it. Yep. Yeah. Those are the conditions for stability, and what we are plotting here is K and mu, and K and mu, these ones. So both of them should be larger than 1, and we're seeing that this is not the case in here.
Trying to boot up my computer, but
Okay.
it's black screen. Nice. Okay. Now it's doing something. Okay, so if we go now to the schematic. So we used mainly series transmission line and short-circuited shunt stub to match the amplifier. And I mentioned that we can use those short-circuited shunt stub also for biasing. So now I would add, let's say 2 picofarad capacitors on each of the matching stubs that you have. My guess is that 2 picofarad is appropriately large for 40 gigahertz operation. Yeah, you can check it from there. Okay, now this.
Which one?
It's the, this is the,
This is the other one.
yeah,
This
the,
is the
other,
first
it's the
one.
design.
This one?
Yep. So we are now talking about the first capacitors after the biasing stub. The first, that one.
You mean this one?
Okay, go one slide actually down, I think. One more. Okay, here. So here we show. So now currently the RF short is done by shorting the line to ground. That's a short. But now we need to add that capacitor, which is parallel to that point. And if that capacitor is large enough, it will short the signal to ground. So it is as strong as the ground because it's an RF signal, high frequency signal. So capacitor will short it. But if it's small enough, lower frequencies will not see a perfect short in that point. So we can add a resistor after the short, which doesn't affect that much to the design frequency because we select the first capacitor cleverly. So the size is large enough that it's short at the design frequency. So we know that resistance adds noise because it's a lossy component. It's the KTB, K times temperature times bandwidth. So it adds noise to the, and it also cancels the signal. So if you can now add, let's say 2 picofarad capacitors maybe to that short circuited.
In this point, well, this one.
put it there in between the ground and the. Sorry?
It's tactile. So you mean in between.
Right.
Which value?
I think 2 picofards first.
So
2000.
I have a question there. I didn't understand very well yesterday. How do you select the value? The ANA? Okay, I understand how you adjust it with the Smith chart, but how you predict a value that is going to be similar to the value?
You mean how do I select the values of length of the lines or transmission lines, or
For example, on the ANA, the value of the transistors.
okay, so that one is in this design. It's a fixed transistor. So it was the one that we have there. So the transistor size is fixed. But in the first few slides, I showed that you can change the size of the transistor by putting now these small transistors in parallel. But these transistors was already sort of selected to have a correct size. But you are correct that this slide now shows sort of the selection of the transistor. That's it. That is where you start. So once this is done, then we match the transistors and the element.
To get the minimum noise and try to get the good amplification. So if you saw
And yet nothing happened, right?
no, it was exactly almost the same. Values
Yeah,
are quite
okay,
the
so
same.
the capacitance value is large enough, right? So if you add it into all of the short circuit, it stops.
Almost the same.
Okay. So now you could add the resistors too, and the bigger capacitance after that. So we would now try to load the amplifier with those resistors, that they are sort of loading the peak that we have. So if you add, typically what I use is for the first gate, I use 50 ohm resistor. And then for the rest of those ones, you can use like 20 ohm resistors. And then put a bigger capacitor after the resistor. Let's say like 4 picofarads. So it's enough large that it will short everything. This is also turning up.
How long is the second capacitor?
I think 5 picofarads. So that can be quite large, but in real world you cannot fit on the chip very large capacitors. So 5 picofarads is already quite big on chip level. You can add them later on PCB level too.
It moves a little, but not that much.
Not that much, but if you put it to all of the stages,
Correct. And this one's 20.
so they are in all stages now. So it seems that doesn't yet affect that much. So we could reduce the size of the capacitors to 1 picofarad.
The largest or the smallest?
The smaller ones, so that it's small enough that that resistor starts to affect our design. So the resistors sort of, the amplifier sees the resistor better. That's a good idea to make it tunable.
So we have them.
Okay.
Now we have C small and C large.
Okay. Try now simulate it. Still doing nothing. Not much.
We can now tune it.
Yeah. So you need to make it even smaller if you have the correct one.
This is the 1001.
Okay. you can see that you cannot make it
lower a
little bit, but you start affect quite, so that you could separate the first gate, because if you lower that one, that will directly affect your noise, right? So that could be a bit bigger, like 1.5 or something. And the rest of the ones that you could left. So maybe 1.5 there, or the other one, yeah.
So this is the first one.
Leave that one as it is, and now try to tune the.
But I can put it at 1000.
Okay.
Okay,
Still the peak is there.
Yeah.
Keep it
2000.
a bit below 1000 maybe. Might be that we need to start a bit too large. 800 maybe. Are we still below 10? No. We need to have it a bit larger. Check my designs too.
And the other one does not affect the other one. I mean,
Check. Do we have similar numbers as mine? Can I drop out? So. Are you sure you control all the correct capacitors? So one way, if it looks difficult, you can add one resistor before the capacitor. So let me see the design itself. So the second shunt short circuited stop that you have, how long is it? Okay, it's quite short. No, I'm talking about that one. So one option is to make that one now longer. That stop, so that it's close to quarter wavelength.
Yes, what are you putting those capacitors on the feedback?
Ah, was it in the feed?
feedback?
Yeah.
Ah, okay,
I
not
put it-
there. Okay,
sorry,
that makes sense.
I did it wrong.
Okay, good.
Shit happens. Yes, sorry about that.
That's a good point.
That's totally right. Maybe I
Yeah,
have
that
another
might-
one in here. Yes, this is the problem of the copy paste thing.
Okay, let's try now. Okay. So your professor knows how to design. Okay, now we are a bit safer now. So what is the size of, you can see that now the peak is getting smaller and smaller, right? So this is where we can control the sort of the unstable areas. The thing is that now it's lifting a bit of the noise of our design band too. So now would start sort of, you would need to play with all of these components that you have and flatten the response. Which one is that?
This is the first.
Ah, that needs to be large enough. That affects the noise a lot, as you can see. But it could be 2 picofarads or a bit less. But that also affects the stability. But now you are below 10 kelvins, right? In the noise. So the first resistor is affecting directly the noise. So that's why the first capacitance needs to be large enough. And then once you have gain from the first transistor, you can use those ones. It can be even smaller, 0.8 or something. 500 might be 2. Yeah, now it's getting better. But you already see that now you're affecting the noise. So between 1 and 0.5 picofarads. I would put that. So now you would need to start. So if we now look at the stability of the amplifier, how does that one look? If we fix it. Okay.
Yes.
So now it looks stable, right?
Everything is on top of one.
No. So now would be the part that you would start playing with the components that you have to get it flatter and flatter without sacrificing the noise. So there is an option that might take some time. So we could maybe switch to my screen now.
Can you share the screen?
So what is the design requirement, Mikko, in terms of bandwidth, for example? For this design?
Okay, so we started from looking at Pospies-Chalsky's paper. So we designed an amplifier covering 26 to 40 gigahertz.
26 to 40.
So I guess that would be our target. I have to say that we cannot do it in 2 hours. So it needs some tuning work, but now you have seen how you can first match the amplifier to optimum noise. Then you know how to stabilize it. And now it would be time for tuning. So you tune the components to get the correct response as you wish to have. And that needs some hours to work with. We cannot do it in this 1 hour or 2 hours, but we are quite close of getting it. So are you seeing my screen now?
But we could optimize it using some kind of optimization tool.
You can do that one too. I usually myself play by hand, so I tune them by hand. So maybe the last tiniest digits you could use optimizer. The problem with the optimizer is that first of all you need to know the different optimization routines that you select the correct, because you know there are many ways of optimizing. One is the min-max, some gradient optimization. So if you are close to local optimum,
Gets stuck.
you miss the
Global.
maybe the best optimum. But if you know very well what you are, or you have done several designs, maybe you know what you are expecting, so then you would quite fastly make that routine available. But I'm not using optimization very often, because once you do it tuning by hand, you also see what if the design is very sensitive to some component changes. So you can immediately say, okay, there is something now with this stop. If I change it a bit, a lot of things change. So then you might maybe make another type of matching network, add some components or go a different way.
That is really, really unstable in the sense of manufacturing.
Yes,
quality.
that's one thing, that something changes, it would go fast away from the other. Okay. problem that it's
It's working.
cropping off this.
You're connected
Okay,
to the
now.
VPN.
Yes, because I need the license from our server. So I have a similar type of a design, as you can see. So this tuning took me 1 day. So I started from the same, or I had the same component as Mikko, of course, because I told him to put them there, but it took me a day to get the following response.
Well, I think people didn't saw ADS previously, so maybe.
Yeah, this is a different software now, but the calculation routines are quite similar, so it looked like a bit different. Even the components are quite similar, so in that sense there shouldn't be any changes happening. So what I added here, so let's see first the response. Zoom in a bit. So now, as you can see, it's getting a bit more flatter. I actually have even more gain, which I will show soon. There is still a bit of a peak here. That would take another day maybe to get that one down. The noise is below 10 Kelvin at middle of the band, which is good. Still, there's some improvement in the matching. So I would say that after a few days, I could be happy with the design. I try to show it on this scaling. This go there on the right. It's not good.
Really slow, the internet.
I
went
dropped
out.
down. So if we would now open up the paper that we are getting the transistor model. So I hope we are close of the noise that Postbit Chelsea was getting. The Jansky paper.
Por internet o la nube? ¿Puede ser?
The Jansky paper.
I think 41 meters.
The figure with you reach noise temperature gain, there was one figure. I already dropped down from the.
Can you
connect
to
the lower one?
the lower?
That's KA band design, right?
Yeah. You have better connection there.
I can open up it here.
Hear me?
Yeah, so we are pretty close, right? I will open up the paper here. I think that, okay, you have. So if you go a bit more down, that figure is a KA band design, right? So the one thing is that we are having a two-stage design. I think it has to be at least a four-stage design to have the gain that they are having. But actually, if you add one more stage there, you have more freedom to play with the matching between the stages, right? So it could be even easier to get it more flatter.
Adding more and more.
There's a limit. If you have very many stages, there's this rule that is it border plot rule that you get more gain, but it gets narrow. But it's doable. I don't see any problems. So here, this is a measured result and designed result. So the noise temperature model is showing a below 10 Kelvin gain. It's the brown one. And they have measured the red one. So, and we are now simulating similar values. So I think we did pretty good in a few hours. Of course, we would now need to model all of the components in like using MIM capacitors and vias connecting the top metal to the bottom metal, but they are usually quite low loss components, so it should be doable. So I will try to share the screen again. So what I did with the tuning here, the input matching is quite similar as Miguel is having. On the second stop, I actually added a resistor here. You can add a resistor after the first stage if you have a long short-circuited shunt stop, because as you remember, if the short-circuited shunt stop is quarter wavelength, it actually shows a large impedance at this point. So you basically can add a resistor there to even more stabilize the amplifier. I use 0.8 picofarads capacitors. What else? Then I have tuned using the matching components here quite a lot, but they are on the same, I think, ballpark as yours, right?
More or less this. But this new capacity, the resistor that you have, oh, went up.
Yeah, you can try to add it there.
What's the reason for that? The stability?
Yes. That affects a lot of the stability. But you need to have a longer shunt stop because to make it close to the quarter wavelength, right?
In order to make it, yeah.
Okay.
The problem is when you did the optimization.
I didn't do optimize. I did tuning.
Yeah.
Okay. So Smith chart, our friend, right? Something like this. So here is a short. That's short. Here is open. And when you have a short-circuited shunt stop, if it's 1 micron long, so you are close to short, so you are here. Right? When you make it longer and longer, you will start to add inductance. So you move on the, if it's ideal shunt stop, you move on the edge of the Smith chart. Finally, you will reach the open once it's quarter wavelength long. Quarter wavelength. That is 90 degrees, right? And then another one would be that you are back there. So that would be half wavelength. You would go back to the short. So now this is an open, ideally an open, looking to that direction. So that impedance is now high, very high impedance. Z super high. So now we have the transistor here. There was input matching network. So what I can do here, if that impedance is looking very high, I can actually add a resistor here, right? Because it still looks high. So it means that the signal doesn't want to go there because it's a high impedance, right? So it will continue to go to the next stage. Another way of calculating it, I guess, that it's a parallel resistance. So isn't it so? Now we are in the danger zone because I don't remember all the basic equations. So how does the parallel? We have two resistors in parallel. How does it? Is it
R1 times R2 divided by R1.
R large? R. This is R small, right? It's not like super R small. I hope this goes correct. Those are the R large plus R small, right?
Yeah.
That's divided. This is super high, then this is R large, right? This is overall R large.
And the concept, and if it's
Large. And they cancel. Okay. So we are left with R small. So it goes there. Both on thinking how of the way the signal wants to go, and even in basic circuit there. So that's why I can add it here.
So it must be, what is it, like what, 20 times the series resistance, something like that?
Maybe. Yeah, that would be a good rule of thumb. But this has to be a bit long, that if you are not loading it here, because then it would be zero. And now this is for the design frequency. So any other lower frequency, this becomes shorter and shorter, right? And at 1 megahertz, this is nothing. 1 megahertz. So you're actually loading it with a resistor, very low frequency. So it will stabilize your circuit a lot.
no oscillation.
So that's one other thing that you can use. Actually, I needed to use it because I couldn't get rid of that peak. So do you want to try it there? So
Just here.
yep.
So large enough, maybe 15.
Yep.
Really flutters.
The noise is getting a bit worse, so maybe the line needs to be a bit longer.
The one that is in between. This is too much to say 1000.
need to look at the noise too at the same time.
This one.
Yeah, that has to be longer. But of course, remember, it will affect a bit of your matching too.
So we have L and M. Put 50 and we increase it.
Okay,
As long
there you go.
like such as it's kind of sensitive.
Yeah, it is because it's on your almost on your single path.
Changes.
So now, this is one thing. If we would have a 3-stage amplifier, we could put it on the third stage, so it wouldn't affect the noise that much. So now it's a bit affecting the noise, as you can see, or quite a lot actually. So at the lower end of our band, the noise shoots up. So something is affecting that one. I wonder if looks
So
pretty
what's
good.
the value that you have in fact in your simulation?
So mine is 20 ohms and the stop length is 800 microns.
20. Hmm. 100 really
800 microns is the length.
eight.
800, so close to the quarter.
something like that, but yeah, increases also this peak.
Yeah, but that needs to be handled with the other parts of the designs. Okay, your noise is now 10. It's pretty good. So, and what I also did is that I actually decreased the feedback of the second stage to get more gain out of it.
So feedback of the second stage, that is not the second.
Second stage. But there we need to be careful since it affects the stability quite a lot.
Too large. Wow, it changed a lot. Putting
I think it's too long now, right?
which is the value? This one is it the value? They put it quite low. Yes. Ooh.
Oh, now I don't know what is
No, I changed something that is really not good. Not good. Let me see. I put it. No, but it is millimeters. Should be 0 point something. Okay. Okay. Now it was like huge
Yeah.
thing. Okay. See that what happened was this.
But if you make it a bit shorter than the 150, you get a bit more gain. But then you increase the peak, as you can see. You have many places to play with it now. So I ended up to have 120. So 30 micron decrease. And now you are close gain of 15 dB, right? So I think those were the things that I did. And then I played with all of the different components to tune it.
Basically now is step by step, one by one, changing them in order to get
Yeah, to see which one affects which one. But I guess that's homework practice. We don't need to do it here.
But one interesting thing is that
So we still have the peak, but as I said, you just need to tune it away with the stuff that we have here.
I'm finding which is a better trade-off. If you will have, or you will require large bandwidth, then you will do different things.
This is already quite large bandwidth.
But you could even
Covers the whole waveguide band, I think. KA band.
Because we intended for 40.
From 26 to 40.
So it's
Almost there, but it needs more tuning. It's not ready. But we know what we are doing, right?
Oh, let's
Okay, I think that's it shortly about the LNA design.
do you want to try anything else?
I'm quite happy. Do you want to know something more?
Yes, a lot. And all of them. I don't know if there is anyone with any question also.
There is some question in the Zoom.
Let's see. Maybe there is someone in the Zoom who has any question, but it seems that not. So in order to finalize, in fact, we have done all the different steps in order to get more or less, which is the whole thing.
And here you can see also someone is maybe wondering, I have a series resistor at the output.
Yeah, indeed.
That can be also used because before that one in this design, I already have 20 dB or more gain. So the resistance doesn't affect anymore the noise performance, right? But that will stabilize again the circuit very much because it's a series resistor for all frequencies, right? And it also improves the output matching quite significantly.
Okay, cool.
And then for very low frequency stability, there are some more serious resistors on the network. But
yeah, those one in particular that are on the upper section, those are even larger than the.
Those are also small value resistors, but they are used to load. So when we assemble this chip to, for example, a carrier or PCB, we wire bond it to a PCB where we have a biasing network. And there we can have larger capacitors. And those are intended for very low frequencies. We talk about hundreds of megahertz or below gigahertz. So then that resistor starts to play role there, the second one. So the capacitance makes a short at very low frequencies, and then it will see both of the resistors actually in series.
And I guess that in fact we have covered almost everything, but we didn't put this.
Yeah, those we didn't do, but we made a decision based on this figure, which was the previous one, that the T-gas min and noise minimum are below 50 gigahertz, close enough. So we can use the traditional equations or the matching or the equations that you see directly in the textbooks.
The stability, in fact, has provided such a good response. So it's entirely stable. And that is, I guess, because previously we had this kind of behavior really bad.
So that below 30 gigahertz, that we have handled now with the resistor capacitor networks. We load it with resistors. So now it went up.
And in fact, that is, we didn't saw in AWR those circles. Nevertheless.
You can draw them.
Let's try.
Yeah. So I think there should be. We go to the graph where we have the S-opt, remember already?
We have.
It's here.
Yeah, this one.
Is this one?
Yes.
Let me check.
The only says
So there should be a.
40 gigs.
If you go wherever you can now add stuff on the Smith chart. If you open that one, add measurements. So we go to the noise, right?
That is linear and noise.
Noise.
We have.
The circle.
What did you find?
Circle, not noise.
There are
indeed.
circles. Okay. Noise figure circle.
Okay, this is gain. Gain.
Yeah, that we want.
And that's zero.
Which is the one? Okay. Noise figure circles. And we have number of circles from port to port. And we want one first. I mean,
Put 3 circles. And I think the step is, it's now, we are now talking about Kelvin, so that has to be 0.01 maybe. Yeah, that's a figure, so it's in dB scale. Let me see, I have put it in mind. .3 dB steps.
and we add it. So we recalculate. Ooh. Okay, maybe.
So you need to do it at 40 gigahertz.
Yes.
And actually it's doing for the amplifier now, if I can see. So you need to
Also
do it
just,
for
yes.
that.
The working and only selecting the 41. Okay, 1, 2, and 3. Oh, huge ones.
So you need to make it.
But this is the S1 one.
Oh, sorry. 0.02.
Okay, this was.
Yeah, then it makes sense because it's in dBs. I was looking actually available gains. Okay.
Yeah. And this is at
But
the first port.
then it should need to be around the S-opt.
1 second. Remember that this one is noise figure at the port 1. So it's a really adapted. No?
So what do you give for the noise optimum, S-opt? The purple point.
Yeah,
What do we give?
Maybe it's not for the LNA working, it has to be for the transistor.
Itself.
Transistor, yes.
Ah, yeah, okay.
So now you have
Okay.
matched it. So all the circles are around the
Exactly,
center.
it's on the center. That is supposed to be, but we will do it for the transistor.
That's a transistor.
But
Exactly.
remember that the transistor is not the one, it's the transistor LNA, because the other one is a 3-port, and this is a 2-port.
Okay.
We need the
Makes
2-port
sense to me.
thing.
Oh, there you go.
Okay. We are back. So we are seeing that circuits are surrounding the one that is in fact is zeta mn, that is the optimum impedance for noise match. And that is
It's 0.02 dB.
yes.
How much is that in kelvins? How do we calculate?
And indeed, we can do the same for the gain. We could get from the LNA, which is the available gain or the power gain. Which
Okay.
power gain?
So you taught us which one is which.
Yeah, this is a very complicated thing that I will let you all remember. We had plenty of formulas, very nice one. The transducer power gain is the most used one.
So
And the transducer power
did you
gain,
figure it out?
I don't know which one it is.
It's actually the available gain circles. That is for the input.
Available gain cycle, which is Gmax. Available gain cycles, this one should be there.
What is the other one? Is it referred to Gmax? Okay, so I think this is using Gmax. Yeah, I think it will put the center point and then you again make steps, gain steps around it. So that would be the 0.3 what I told you.
Let's see if it works. And this is the LNA itself. Okay, maybe I need to figure out at which frequency. And okay. This center is different from the center of the noise,
Yes,
as we already know, because we optimize for noise,
Noise,
and not
exactly.
for gain. Also, we could plot the stability circles, no? Do you know if they can be plotted here, Rodrigo?
yes, you can.
Another tab on, yes, for stability.
This one?
Or is it in circles?
So it's not in stability circle or primary one.
Yep.
Okay, we found it. And in this case, only for the LNA and at the frequency that we are looking at. It does not appear here
And the reason is what?
because at this frequency it's a really stable.
Yes, so we can reduce now the feedback to
Ah.
see what happens to that switch.
So let me close the other one. Because we already figured it out. And in this one, make it too low.
We can tune, yes.
Let me. And then we can go here and see what happens. Oh, well, I tune it and I changed the optimal values of everything, in fact. But I'm trying to see if the stability circles upper like 1 millimeter. So let's see.
So that, oh, you are going a bit wrong direction. So 150 micron was already that it was stable. So if you go smaller,
Even smaller. So let me 0.1
That's the upper. Yeah.
Yes, in order to make it lower,
Yeah,
so
yeah,
I can
yeah.
have a
So there's zero, yeah.
sorry, better control of it. Let's see.
Circle is not shown. It should be between of the. Are you sure you plotted the stability circle? Should appear when it becomes, if you make it now larger.
Oh, no, so it failed. It's in the error. Actually.
It's in
There's
there.
an error about this.
It says so?
Yeah.
Oh, yeah. yeah. I cannot see a thing. So 1 second. But 1 must not be the same code as G.
Oh, it's
Okay,
No.
let's see what this means. Stability set report 1, gamma. Gamma.
try to.
Yeah, this is what I was thinking, but I didn't.
Ah, there it is.
Here we go. Okay, and no error. And I just say if we lower
Yeah.
it, we make it much worse at the frequency of 40 gigahertz. But if we increase it, it's outside of the Smith chart. We remain outside of the Smith chart. So this part is unstable and this part is stable.
You can plot that one too. It will tell you. So if it's inside or outside of the circle. So there's you need to check it.
Which one is the S11?
Which one is the stable area? That's sure. That green is a circle. It's a big circle now. It looks like it goes around the Smith chart. So now there should be a command that tells you which part of that big green circle is stable, inside or outside.
Well, I think that this is the gray. I mean,
Or does it show it there?
yeah,
That's
those are
clever.
the points.
Okay.
Those are the points.
Okay, that's
If you reduce the feedback, I think you will get in.
Okay, I put this 0, so this is
So I
no,
guess-
not at all. This is
The fact that those are like points on the top side is showing where it is shaded.
it's unstable. Yeah. So now the circle green inside the green circle is unstable region. So if you would match the transistor with that impedance, it would oscillate.
only to let people know, this is now non-existent because it's 0, so it's directly connected to ground. So the transistor itself directly connected to ground without anything else. It's unstable at 40 gigahertz. That is. We made it.
Can you get them? How much feedback do you need that you
Take it out.
put a bit more? Okay. Is the S opt and where is the S opt? No, they are not.
It's not here, but we can plot it also.
But it should be inside the noise circles.
You mean the sigma opt, so the minimum
Minimum
Noise
noise measure. So you can now see that with the certain feedback, you can put the gain match, which is the conjugate match in this case, because the transistor is unconditionally stable, and the S opt on top of each other. So your matching would be good and your noise would be good.
almost inside one of the other, or one on top of the other. Something like that. Not exactly all of them, because you say that not all the circles have their own,
No, I'm
Center.
looking at the centers.
but they go split, they separate a little. So if you want to really reach it, you reach only one of those. This one. You see?
Where are the points? So if you put it without feedback,
Without feedback, I don't know.
yeah. Where are the points? Okay, and now you bring them closer together. There. That was close enough, right?
Yeah, in fact, this is similar where we were placing, maybe a little more higher.
Yep.
This one, P1.
Get it? Why do you have so many points there? But should be only one optimum.
But we have plotted 3 different sequences.
No, you should have the. If you are plotting the S opt, and then you have circles around it. We have one optimum and circles around it. I don't know why you have.
But the circle is center.
Can you open up my slides?
Okay.
Are they there?
Those ones.
That. So you can see that I only have one optimum and 2 circles for the S opt and 3 circles for the gain. There's one optimum for the gain.
But this is the global optimum, but not the center of the circles.
It's showing center of the circle. I see. Okay. I see.
So in fact, what we are seeing here is a mess of circles and centers. of circles.
Okay. So those I wouldn't like to see. I only want to see the optimum and the circles.
Okay, but this, I think, I don't know if I can take it out. Let me check. Yeah. Those are the red ones, and I can simply say no.
Okay. Makes sense.
And no, and let's see. It is still appearing something here. Okay, no way of taking it out. Oh,
What happened?
I died totally.
Connect wires hanging around.
Because it's this one. It's here, but let me check. I think that the battery is not going very well. Okay, I went out, but yeah. You can say one word.
What would be the word? Smith chart is our friend.
The Smith chart is our
As you can
friend. As you can see. And it's dangerous to play with it, but it's so fun.
No, it's not dangerous. It's fun.
So I guess that we have covered almost everything, no? Or everything.
Yes.
The only thing that it lacks will be to make the
actual chip.
The actual chip.
That would be another maybe session.
Okay, it went out. I don't know why. So I won't overload it. So I think that is. I don't know if anyone else has any questions or no. Everyone is happy. And I think that we can say goodbye to everyone.
I think so. Okay. Very much. Thank you for your attention. I hope you had some kind of idea of the MMIC LNA design in this short course. I think it's not that difficult as you can see.
So, Rodrigo,
Or Rodrigo wants to say something.
maybe you want to say something
Or
as a
ask
final.
us.
Yeah, that's okay.
Where are the leaves? John Kerry. Like John Kerry. So what happened?
We finished it.
Some success? We declare success.
Yeah, and no, we say that Smith chart is our friend. This is what we say.
Smith chart is our friend, and we should trust him. I think it's been a great experience, Mikko. We really deeply appreciate transferring the knowledge to us, and for us, it's a first experience to go through all the steps, and we'll definitely continue for the students that are here paying attention and that are interested in continuing on this. We will definitely go through the steps in depth, and we will be inviting you in the future if we get stuck somewhere.
Please do.
But we appreciate you both.
And you, so don't go away.
It's been great. So thank you very much.
Thank you. Thank you.
Thanks to you. Rodrigo.
I did already. Come on. Where are the beers? All right, guys. So thank you very much. Muchas gracias. Estamos listos con la actividad. Espero que lo hayan disfrutado. Buena, Patricio. Que lo hayan disfrutado y por supuesto si es que hay alguna duda al respecto de lo que hemos estado conversando y la podemos revisar, están los videos, ya está todo ya subido en este Google Drive, he subido más papers y creo que voy a subir un libro más acerca de diseño de amplificadores del González.
Subiste además un par de papers, ¿no?
Sí, el de Pospieszalski, el MOSFET, MESFET y MOSFET. Aparte de eso, bueno, otro más, no me acuerdo de cosas. Pero hay un libro que es el libro de amplificadores de microondas de González. Y lo otro es el documento tuyo. ¿Ya está arriba? Ah, perfecto. Así que con eso damos por cerrada la actividad. Ahora que se arranca Lenin. Y agradecerle nuevamente a todos los que participaron y por supuesto a Mikko por entregarnos su conocimiento pleno. Así que gracias. Bravo.
Gracias.